undergo this distortion and see these antiferromagnetic ordering because of this reason I just mentioned. But at least some work on this direction has started, even though it does not yet realize this ferromagnet. It's good to see people at least working on these materials, because for the longest time, D4 was just considered to be of no value. So the transition metals on which experiments have been done are ruthenium, osmium, and iridium, and the structures that have been looked at are pyrofluor, double peroxide, layered peroxide, and honeycomb, and these are some of the materials. Gang Chao here has also worked on some of this. We'll talk about it next. What is important is they are all strongly magnetic. They are all strongly insulating and magnetic, and the details of the magnetism are somewhat different, ranging from, ranging from antiferromagnetism, some signatures of ferromagnetism, and spin class. So I'll skip this, but these are some of the references to look at. Let me just show one data here from this is from Jiqiang Yan. He's been trying to make these materials and look at their properties and just looking at the resistivity. And what you see is there's a whole class of these materials. They are mostly metallic, but this particular, usually if the A site is magnetic, it has the different properties, but yttrium, which has no magnetism on the A site, the system then, you would have expected this to be a metal as well, but it turns out to be a fairly good insulator. And more studies on this are needed to conclude exactly what the magnetism is like. This is the example we were discussing earlier, a calcium 2RuO4. This is the close cousin of Sr2RuO4, which shows this beautiful data from B.J. Kim. This particular material is in fact insulating, and again it distorts. There's very beautiful RIX data, and the reason their plot looks opposite to mine, with the 2 being upper in energy compared to the A1G, is because they've made a plot for holes. It took me a while to figure that out, but this is the diagram for holes. In any case, what they show, you would have expected the occupancy of the A1G to be, they are looking at the occupancy of A1G and the EG orbitals, and at the point, if there was no distortion, it would have been 1 here. But you can see they are essentially showing the A1G to be more occupied compared to the EG orbitals. So that's essentially evidence from RIX showing that there is indeed this splitting of the T2G sector, and the A1G orbitals are more occupied. So, okay, so let me then conclude by saying that, we would like to go from a model to a material, but sometimes these models have to be tweaked by putting in certain crystal structures with the right angles for these poppings, as well as distortions. So our job for the next steps are well cut out for us. We want to look at different bond angles and different crystal structures. We want to understand this particular orbitally entangled ferromagnetism through maybe some more analysis of their wave functions. Experiments which might apply pressure to tune the distortion, maybe get rid of it and push it into, this ferromagnetic state would be very useful, as well as XMCD and X-ray absorption studies, which can tell us the occupancy of L and F separately as well as L dot S from the sum rules that you can get from the branching ratios would also be very helpful. So with that, Prithvi, thank you.
Great, thanks. So I guess you have the Ichi orbital as well as the fact that you have much higher energy. But do you expect to get like these phases at nearby and metal insulator conditions? And would there be some like ferromagnetism there? So the open metallic side of the conditions created?
Right. Yes. Even without bringing in the ET orbital, you see, let's say, when you have this particular distorted model, let me go back to that. Yeah, this one. So once you turn on hopping, right, it mixes, if the bandwidth you do hopping is larger than this distortion, then typically what is happening is you go into a metallic state. So like SRRU3 is a ferromagnetic metal. So what one would like is somehow, have an intermediate state where the distortion is not very large, but still U is large enough to give you a ferromagnetic insulator. So right now what happens is the moment, at least some of the materials I've looked at, once the bandwidth becomes, or another way to say it, the distortion generates the bandwidth, right? So if the distortion is small and the bandwidth is large, then the question is, can it still remain insulating? Typically, they tend to become metallic. But definitely, even without bringing in the EG orbital, there is a possibility of getting ferromagnetic insulators. And to answer your question, the ferromagnetic metals are also related. In my phase diagram, I only focused on large U. If I come down to smaller U, there are still ferromagnetic states there. Those would be the best place to look for these ferromagnetic metals.
You might have mentioned this already, but is there some experimental proof that allows you to distinguish the small ferromagnet from usual ferromagnet iron?
Yeah, I think these X-ray techniques would. Because if you look at XMCD, they can distinguish the components of L and F in the particular state, in the ground state.
For example, if you sort of magma dispersion, that would be just the same.
Yeah. I don't think in the magma, like if you did neutron scattering, you can ask Radu about it, but I don't think you would be able to distinguish it there. a vegetable. So double peroxide has two transition metal ions. It's like A2B, prime O6. And usually B and B prime are both, magnetic. But if one of them is non-magnetic, what I call a vegetable, and then an active transition metal ion, some of those have the two configurations, but then the interactions are higher order because you're going from a B prime O